Okay, so welcome to Department of Mathematics, Sagat College, Autonomous Tirupattur. So this is the video lecture, the first video on the program called linear algebra. So the code for this program is M643. Okay, so in this video, we will have a discussion on the group as well as field. Then I will introduce the concept of vector space. Okay. So I am taking A and B are two non-empty sets, and we are familiar with the operation known as Cartesian product. A cross B is a new set which contains of all order pairs x comma y. The first component x is coming from A and the second component y is coming from B. This is A cross B. Similarly, you can define B cross A. In this segment x comma y, the first component x is coming from set B because B is the first set, and y belongs to A. Okay. So for example, suppose A equal to 1, 2, 3, and set B probably I am taking x, y, 2 elements. The order of the set A is 3, order of the set B is 2. The order of the set means the number of element in the set. So here 1, 2, there are 3 elements, so order of A is 3, and there are 2 elements, the order of B is 2. Okay. So now I am writing A cross B. So the collection of pairs, the first is coming from the first set, that is A, and the second element is coming from the second set B. So 1 comma x, 1 comma y, and 2 comma x, then 2 comma y, and 3 comma x, 3 comma y. This is such a collection. So collection of all possible order pairs. Then similarly, B cross A. So first element is coming from set B and second is coming from A. So x comma 1, x comma 2, x comma 3, and y comma 1, y comma 2, y comma 3. So by observation, the cardinality of set A, that is I already said that the order of the set A is number of element in the set. So here A contains 3 elements, 1, 2, 3, and B contains 2 elements. So order is equal to 3 and order of B is equal to 2. So here 1, 2, 3, 4, 5, 6. So this vertical line symbol stands for the order of the set or cardinality of the set. So in the matrix theory, it represents determinant, but here it represents the order, number of elements in the set. So by counting, so we found that the cardinality of the set A cross B is 6. Similarly, 1, 2, 3, 4, 5, 6. So B cross A is equal to 6. So anyhow, the A cross B, the set A cross B having the possibility of order pairs x comma y, and x is from A and y is from B. So here A having 3 choices. So the number of ways to fill this one is 3. Possible ways to fill the first component is 3, and the cardinality of B is 2. So the number of ways to fill this particular place as 2. So if you fill the first place and the second place, you will get an order pair. So 3 times 2 is equal to 6. So this is nothing but cardinality of A into cardinality of B. So both are equal. Okay. So thus by observation, cardinality of A cross B equal to cardinality of A into cardinality of B in the case of finite sets. So in this portion I have introduced the operation what is called as Cartesian product of two sets. Okay. Then get into the concept of group. Okay. So for that I am taking a set G, the non-empty not equal to empty, so be a set. That means G is a set, it contains at least one element, so that means it's a non-empty set. Okay. And I am taking a function that is represented by the symbol asterisk, that is star, whose domain is G cross G. What is G cross G? So the Cartesian product of G with G. So G with G is the set of all order pairs of the form x and y. The first is coming from the first set, the second is coming from the same set because the both sets are same. Okay, so this is G cross G is collection of all ordered pairs x comma y. The first and second element are coming from G. Okay, whose codomain is G. That means I am considering a function star defined on G square, that is G cross G, and whose codomain is G. Okay, this particular function will be called as binary operation on G. Okay, so now I have two items. One is a non-empty set G and another one is a operation, that is a function defined on G square and codomain as G. Okay, fine. So now I am considering the structure G comma star or asterisk. Okay, so the question is, when will this structure will be, okay, structure called as a group. Okay, done. It should satisfy the four axioms. I am listing out all the axioms and I will explain what does it mean actually. Okay, the first one is closure axiom, and the second one, that is associative axiom. Third one is identity axiom, and fourth one is inverse axiom. Okay, the closure axiom stands for, okay, let or probably, okay, choose any two elements, x and y belongs to G. It is possible because G is a non-empty set, so the selection of element from G is permissible here. So the guaranteed by G is a non-empty set. That's our initial assumption. Okay, so then x star y should be the member of G. Okay, so this one stands for the closure axiom. That means you take any pair of elements from G, or take any element from G square. Okay, so do the operation star. So x star y, so it's a new element. It's a new element, and whether we have to check whether it belongs to G or not. If it is present in G for any pair of elements, then we can say that the set G is closed under this operation. G is closed under star. Then coming to associative. So here we need three elements, x, y, z. So it may not be different. It's not an issue. Any selection. G. Then x star, y star z, and x star, y star z. So look at the orders, x, y, z. I'm just only changing the bracket, the order. It will be equal for any triplet. If this particular expression is true for any three elements from G, then we can say that G is associative under star, or simply say that star is associative. The operation is associative. Okay, then coming to the identity axiom. The another sentence for this one is the existence of identity. Okay, that means we are looking for an element in G. That is, so there exists an element, probably I am representing the particular element as E from G. Okay, it's a special element. It has some qualification. So there is an element from G. So such that X star E, that means I am operating the element E in the post direction with the element X, and in the pre direction X, E with the X, the value should be equal to E, it for all X belongs to G. That means we are looking for such element. Okay, so this is X. Okay, so there exists an element, special element E in G. E has some qualifications. That means you take any element from G, whatever element, is not a matter. If you operate the special element E with X in the post direction or the pre direction, you will get the same effect X. That means the operating by E does not affect the element. Okay, so X with E, we get X back. E with X, we get X back. The such kind of element will be called as the identity element. If the particular element exists, then you can say that this particular structure satisfies the identity axiom. Okay, and in the later on the coming lectures, we will prove that this particular element is unique if it exists. Okay, that is the speciality of this particular structure. Anyhow, and looking for inverse axiom. Okay, so in the stage 3, we found an element what is called identity element. Okay, now picking any element for any element, probably X belongs to G. Okay, we are looking for some other element. There exists an element, probably I am labeling the particular element as Y in G. Okay, such that, okay, for the element X, we try to find element Y such that X star Y, I am operating the element Y in the post direction of X and in the pre direction of X also, X, we will get the element E. Okay, so for an element X in G, or any element, a random choice, we are trying to find the element Y in the set G. The nature of Y is X star Y and Y star X equal to identity. Okay, if the particular Y exists for any choice of X, then we can say that G comma star satisfies the inverse axiom. And in addition, so the inverse of X is represented by X power minus 1, that is X inverse is equal to Y. So the inverse of the element is X is Y. Okay, suppose this structure G comma star satisfies the closure, associative, identity and inverse axiom, then G comma star is a group. It will be called as a group. Okay, done. Then coming to this one, closure axiom. So here we are choosing a binary operation. It clearly shows that the order pair is goes to connect to an element in G. So that means, look at the closure axiom. We are picking two elements in G and applying the operation star, and we are checking whether it is belongs to G or not. By our choice of binary operation, it clearly shows that definitely x star y should be in G. So therefore, it is automatically proved. Okay. So if star is binary, then it automatically obeys closure. If G comma star satisfies the closure axiom, then definitely star should be a binary. Okay, fine. So if this particular structure is satisfying this 4 axiom, then this structure will be called as a group. Okay. And in addition, this is the simplest algebraic structure in an abstract algebra. Okay. In addition, there is another one on this, what is called commutative law. So the law number 5, commutative axiom. Okay. So for two elements, which implies x star y equal to y star x for any pair. So that means x with y and y with x are always equal. Then we can say that the operation star is commutative, or in other words, G comma star satisfies the commutative axiom. If G comma star is a group and star is commutative, then this particular group will be called as abelian group or commutative group. If G comma star is a group and it fails to satisfy the commutative axiom, then it will be called as non-abelian group or non-commutative group. Okay, so let's see some examples. So before seeing the example, I will introduce the concept of ring as well as field with the help of the definition of a group. Okay, so from the observation, we came to know that the group is the simplest algebraic structure. It contains only one operation. Now I am adjoining two binary operations. Okay, so let the structure or plus and dot. So here R is a non-empty set and plus is the first operation. Yes, of course, a binary operation, and dot is a second operation, is a binary operation defined on R. Okay. Anyhow, for a group, it is satisfying the 4 axiom. One is so closure axiom. For the second one, associative axiom. Third one is identity axiom, and the fourth one is inverse axiom, and fifth one is commutative, is a special one, commutative. Okay, if the particular structure satisfying the first one alone, then it will be called as quasi group. So quasi group, if it is satisfying 1 and 2, it will be called as semi group. If it is satisfying the first 3, is called semi group with identity or monoid. And if it is satisfying the first 4, it will be called as group. The first 5 is called abelian group. Okay. If the structure G comma star satisfies the first one alone, it will be called as quasi group. With the first two axioms, it will be called as semi group. First three axioms are okay for this structure, then the particular structure will be called as monoid or semi group with identity. And if it satisfies the first four axioms, this structure will be called as a group. And if it is a group and it satisfies the commutative axiom, it will be called as a abelian group. If it fails to satisfy the commutative, and it become a non-abelian group. Okay. Now look at this structure. So I am changing the symbol to F. So here F is a non-empty set, and plus is the operation, binary operation on F. Star is another binary operation on F. Okay. So look at the structures. Okay. The first one, F comma plus is an abelian group. That means it obeys these five axioms for the set F with respect to the operation plus. Here the plus represents the first operation. It need not be addition, it's the first operation. And okay. In this scenario, since it is an abelian group, look at the so axiom number 3 is an identity element, and this symbol will be called as addition. This will be called as multiplication. Here the addition stands for first operation, multiplication stands for second operation. So in this scenario, the 0 will be called as, because the axiom number 3 guarantees that there is an identity element, and I am representing the identity element in F with respect to this operation will be represented by 0. 0 is the symbol as an identity element, is a representation. Okay, 0 is a representation of the identity element in this structure. Then second thing, I am considering the set F except 0. So 0 means the identity element in F with respect to the first operation. So I am punching out this identity element from F, and I am adjoining the second operation dot. Okay, this is the new structure, non-empty set, okay, with a dot. If it is an abelian group, okay, then in this scenario there should be an identity element that will be represented as 1. 1 is an identity element. Here the symbol 1 stands for the identity element in this set with respect to the second operation. Okay. So if the 1, 2, that is F plus with is abelian group, and this one is an abelian group. Abelian group means it satisfies these five axioms. Then third one is what is called distributive property or distributive law. In this scenario, the second operation is distributive over the first operation. That means, so x and y and z are the elements of this F. So y plus z and dot. So this dot stands for the second operation, the plus stands for the first operation. This guy is equal to x dot y plus, that is second operation, and the first operation x dot z. It works for any triplets from the set F. Yes, it's possible because F is non-empty, and here the dot is in the left side, so this particular expression will be called as a left distributive law. And similarly, okay, so y plus z dot x, that is here the dot x is on the right side, so y dot x plus z dot x, it works for any triplet from F, and this will be called as a right distributive law. That is, we are just multiplying y with x, z with x. Okay. If these two expressions are valid, we can say that in this structure the second operation is distributive over the first operation. Okay, this is the structure if the condition number 1, that is f plus is abelian, and 2, this one is an abelian group, and third one is distributive law, these two are hold, then it will be called as field. Okay, so this structure f plus dot plus is the first operation, dot is the second operation, and 0 represent the identity element with respect to the first operation, and this number symbol 1 represent identity element with respect to the second operation. Okay, so from this choice f except 0, the 1 is the member of this one, so this argument evidently shows that 0 should not be equal to 1. So in the field, the identity element with respect to the first operation and the identity element with respect to the second operation, in simply speaking, additive identity element and the multiplication identity element are not equal. It is guaranteed by this one, because one is an identity element of this set, one is the member of this set, and this set doesn't contain 0. So this argument shows that 0 does not equal to 1. If the particular structure satisfies 1, 2, 3, then this structure will be called as a field. And in addition, suppose that in the second thing is an abelian group. I'm just removing this one, abelian group. I'm replacing the word semi-group. Then this structure will become a ring. The structure ring. Okay, anyhow. So every field is a ring, but the ring need not be a field. And some famous examples of a field we're going to discuss is OR, set of all real numbers, plus stands for usual addition of real numbers, and a dot stands for usual multiplication of real numbers. And here number 0 is acting as a additive identity, number 1 is acting as a multiplicative identity. You may check all the possibilities, because OR comma plus is an abelian, OR except 0 with multiplication is abelian, and the distributive law is valid. So this particular structure become a field. Since OR contains infinite number of elements, so is an example of infinite field. Similarly, C stands for set of all complex number. Okay, so plus dot, here the plus stands for usual addition of complex numbers, and the dot stands for usual multiplication of complex numbers. Is also infinite field, example of infinite field. Okay, so sometimes this particular field may be called as field of real numbers, and this algebraic structure field will be called as field of complex number. Okay, so in the upcoming video I will introduce the concept of vector space. So to define a vector space, we need a algebraic structure field. Okay, so my interest is to define a vector space over these two fields, that is the field of real numbers as well as field of complex numbers. Okay, so thank you for watching the video. So in the next video we will see you again. Thank you.